This is like a generic equation that if I was not at the melting temperature, I could still use an integration about like a differential scanning calorimeter curve to sort of get a delta H. But yes, to make it easy for ourselves, we will always think of it like this. This is at the melting temp. And from there, we can use these equations to adjust. Yes? I have it written both ways, actually. I took them off here because this is a situation where standard state, I'm saying like it's at a different temperature, right? And so I don't know if everyone recalls earlier, once upon a time, I said standard state was 1 atmospheric pressure, 1 molar concentration in 55 molars of water, or whatever. That was our situation for biochem. And then I said at some temp. And I said, generally we call it 298. I might have to give it to you. This is a scenario where, yes, like this is relevant because everything else is the same. This 1 molar concentration is still holding true. The 1 atmospheric pressure is still holding true. And temp has changed. I'm just trying not to confuse people when you get 298K as standard state in some other class, like hard and fast. But yes, all your other standard state things are same. 1 atmosphere, 1 molar concentration, pH 7, all the other rules. Okay. Yeah, that works. That's how I have it written, and then I like, what do I do with my notation? All right, so these are corrective terms, like I said, and so just quickly recall that delta H and delta S were temp independent for Van't Hoff, okay, which is not a real life situation, but we had a Van't Hoff equation and a Van't Hoff plot that let us think about how equilibrium constant would shift with temp. This was natural log of KEQ versus 1 over T is how we plotted it, and we saw something that looked like this. Slope was equal to negative delta H over R. The sign of delta H dictates what this line looks like. So if people have done the homework, it might not be sloping down. That's okay. What is the sign of delta H? This negative is always here. Exothermic, endothermic might look different. No big deal. Intercept was delta S over R. Okay? Van't Hoff assumes delta S and delta H don't change with temp. The reality is they do. Okay? And so these are kind of corrective terms we need to actually adjust for the temperature dependence of these things. So finally, the one I care about most, what is the free energy of unfolding at any temperature of interest to me? This is this whole piece. I'm too lazy to write them in, my apologies. This whole piece here, right? All this whole term minus the temperature I'm interested in times this whole piece here. There it is. It's kind of a lot of numbers. It's simple math. You can do it. Okay? This lets me solve for free energy of unfolding at any temperature. It tells me protein stability. Okay. Any questions about that? Yep, Don? So the baseline is just, I know that because of some interactions with water going on or whatever my buffer is, when the protein is unfolded, which is sort of on this side of my curve, I have a different heat capacity for the folded protein. This is folded proteins in water. everything is sort of heating up, just kinetic energy. But what it takes to heat up folded proteins in water and what it takes to heat up unfolded proteins in water is slightly different. And so the baseline is just, let me set sort of a bottom line here where basically whatever that heat capacity is, it depends on how many are unfolded and folded. I'm just putting a function to the bottom of this. You could draw it flat across if you wanted. The other figure I'm about to show on the slides uses Cp of folded up to the melting temp, and then does a step function and jumps up and uses the other side.
So when you have Cp is the F plus U in the superscript, that value is always 1, right? Because it's F plus 1 minus F?
That notation is just to indicate what the base, like there's some baseline I'm using. It's not actually adding them together. We'll look at when I go to the slides, we'll bring up a picture and hopefully it'll look a little clearer. You could, I mean, like I said, any line you draw there would maybe work, just like a flat line or just like a straight line, even that doesn't have a function associated with it, just like connect the 2 points with a linear. You would get a pretty good estimation with that area of delta H, which is all I'm really trying to get off of this, is set myself a bottom so that I can get that approximate enthalpy change. Okay.